Boom. Green flow. Hello and welcome back to differential equations. There's no more energy here left right towards the end of the semester. Everyone wants to pass out, including me. I think did I change the title? Yeah, I did. Good. So now we're going to utilize our awesome knowledge of matrices to solve differential equations using the eigenvalue approach. If you want to know more about eigenvalues, eigenvectors, eigenfunctions, you take linear algebra and learn the details. Over here, we will start with the vector of derivatives times the matrix times the column vector. That was that A was labeled P earlier. So technically this would be like x prime y prime is equal to sum A, B, C, D times x, y, if you want to translate that into the system. But then also what you need to realize here also what you need to realize here that this is a system, right? This is a system of two equations, but we could have as many as we want because it doesn't give us a bound on how many unknown functions we can have. So this could be 3 by 3 system for A, could be 4 by 4, 5 by 5, or whatever higher order. So now what we are going to do is we are going to assume solution of the form x is equal to some vector v times e to some lambda t. Lambda is a Greek letter, which is equivalent to our lowercase l in this case. And this lambda is eventually going to be that special eigenvalue. So now what I do is I substitute that in my differential equation, but before I can do it, I have to take the derivative. So x prime will be lambda v e to the lambda t. And now plug in. So what we get is lambda v e lambda t is equal to a times, and instead of x I have v e lambda t. Now remember that you can't divide vectors, but you can divide a non-zero functions, in which case we can cancel these guys because they are non-zero functions. Right? E to the x is always larger than 0. So they can't reach 0, so we're okay. That leaves us with the lambda v is equal to a times v, and you cannot divide by v, so you have to leave it there. And what you can do is you can bring everything to the same side and then do some factoring. So you bring av minus lambda v equals to the 0 matrix, and then you can factor out a minus, and now there is a trick over here. You have to multiply by I. So I will explain that. A is a matrix. this A could be 2 by 2. Lambda is a constant, like number 7. And you can't multiply, you cannot subtract A minus 7 because they don't have the same dimension. Number 7 is a matrix that is 1 by 1, right? Because it only has one entry. Technically, you can think of any number you know so far as the 1 by 1 matrix, right? So number 7 would be 1 by 1 matrix. So if you have 2 by 2A, like we had earlier, and you want to subtract lambda from it, you have to multiply lambda by identity matrix, and identity matrix takes on the size of whatever matrix A is. So if you did this with a 3 by 3 system, then matrix A would be 3 by 3, and then you would have to use 3 by 3 identity matrix, which has all the ones on the diagonal, everything else are zeros. So now that you have this, right, you can take the determinant, because vector V is a non-zero vector, which means that A minus lambda I must be equal to 0. And then if you take absolute value, which is actually the determinant, in this case, you will just get a 0 on the other side. So this equation that we just derived is the equation which calculates eigenvalues. So use this to calculate eigenvalues. And then go a few steps back to go with A minus lambda I V equals 0. So use this one to find your eigenvector. So technically what you are learning are those two formulas that are boxed in, but then you can also learn the derivation and then use it, if that makes you happy. So now, what is the eigenvalue solution? Eigenvalue solution of this. So if you have a system of differential equations, the eigenvector associated with the lambda, the solution is given as V e to the lambda t. So lambda is the eigenvector associated with eigenvalue lambda. So V is an eigenvector associated with eigenvalue lambda. So this is what we want. let's see how it's used. I'll solve, I guess, maybe two 2x2 examples and then one 3x3. That should be sufficient, right? So let's go. We have x1 prime is 4x1 plus 2x2, and x2 prime is 3x1 minus x2. So immediately the matrix for this is x prime is equal to 4, 2, 3, negative 1 times the vector x, which is x1, x2. So that transforms my system into the matrix, and now we have to use a minus lambda I in the determinant. So the determinant would be matrix A, which is 4, 2, 3, negative 1, minus lambda times 1, 0, 0, 1. So we're looking for that determinant. That's going to be the determinant of, so remember, component-wise, lambda distributes for both ones. So you have 4 minus lambda, and then 2, and then 3, and then lambda. Wait, why did it disappear when syncing is off? So 4 minus lambda, 2 minus 0 is 2, 3 minus 0 is 3, negative 1, it's negative 1 minus lambda. Yep. So now you see you have to FOIL, and then minus 6, which is the other diagonal. And all you need to do now is to just FOIL everything, subtract 6, and you're done. So when we FOIL, I have negative 4 lambda, plus lambda squared, minus 6. Put it in the decreasing order, so lambda squared minus 3 lambda minus 10. And that further breaks down into lambda minus, what would that be, 2 and 5? 2 and 5. So yes, negative 5. So lambda minus 5, lambda plus 2. Yeah, say it's good. Okay. Equals to 0, from where I get lambda is equal to 5 and lambda is equal to negative 2. These are your eigenvalues. Next time someone tells, yeah, what do you know? You can find eigenvalues now. What happened?
I could have had 100 on the linear final, but I changed all my answers for the eigenvalues from negative to positive, or like the ones that were negative actually to positive. I changed the signs at the last second because I was like, yep.
All right, so now we have two eigenvalues. Now, guys, these are the exponents on E. So this is going to be your e to the 5t and e to the negative 2t. So we have those. What we are looking now are those vectors in front. They're coefficients, right? So that's what we're looking for. Okay, so now what do? I found these two values, and I'm going to start with lambda equals 5. So I want to come up and find the eigenvector for it, for lambda equals 5. So when lambda equals 5, I can bring that 5 and put in a matrix. So look at the matrix 4 minus lambda and 2 and 3 and negative 1 minus lambda. Let me just verify that. Yep. And just plug in. What you get is the matrix which has, when you plug in, negative 1, 2, 3, and then negative 6. I hope you see that these rows are multiples of each other. See that? These are multiples of each other. If you multiply the top row by negative 3, you get the bottom row. Eigenvalues will always do that. So when you are solving these things and you run into a situation when they are not multiples of each other, it's wrong. Then you have to redo it. So that's a check for you. Now, you want to solve this system, but there's nothing to solve because it's an underdetermined system. You don't have enough, right? You have two variables, you don't have enough equations to solve it. So what you do is you would say that you're asking yourself which vector, put A and B there, will get you into a 0, 0 on the other end, right? So now if you want to, you can solve it as a system. You can solve it any way you want, right? Some of you might even guess that A is equal to 2 and B is equal to 1 just by looking at this, because that's how it works. I don't know if you can do it just by looking at it, but the goal is to figure out what A and B needs to be in order for this to hold. So you can actually create the system of negative A plus 2B equals to 0, and 3A minus 6B equals to 0. Now, since these two equations are multiples of each other, you don't have to keep both of these. So you can just strike one equation out, and then you get the equation A is equal to 2B. So I usually pick, right? You can pick, because this is 2B, you can pick B equals to 1, which means A is going to be 2, and you get your 2, 1. You can always do that. So we have one of our vectors to be there. So my first solution, x1, is going to be e to the 5, lambda is 5, so 5t. Oh, I forgot the vector. Oops. So 2, 1, e to the 5 lambda. Now you repeat the procedure for lambda 2, negative 2, right? lambda negative 2. So again, we have 4 minus lambda, and then 3, and then 2. No, 2 and 3. And then minus 1 minus negative 2. So what I get here is 6, 2, 3, and 1. Immediately check if calculations you did so far are correct by making sure that the rows are constant multiples of each other. And apparently they are, because if you multiply bottom row by 2, you will get the top row. So they are, in this case. So what you can do is you can immediately go 6, 2, 3, 1 times AB to give you 0, 0. Now, if you see that your answer should be 1 and negative 3, you're good to go. But if you don't see, just write it out. So you have 6A plus 2B is 0, and 3A plus B is 0. Since these equations are dependent, I'm just going to strike one of the equations and realize that 3A is equal to negative B. So if I pick A to be 1, B better be negative 3. So x2 solution is going to be 1 negative 3 e to the negative 2t. Right, lambda is negative 2. But wait, there's more. Now all we need to do is to put this in an overall solution, and this is what I erased earlier. Overall solution x is the superposition of the two solutions we have so far. So C1 times 2, 1 e to the lambda is 5, so 5t, plus C2, we just found the negative 3, 1 negative 3 there, and then e to the negative 2t. This is the solution. This is the general solution. The general solution. All right, so I hope you guys can follow the pattern. I'm going to put one of these problems for you to enjoy. So x1 prime is 4x1 plus x2. x2 prime is 6x1 minus x2. Go. So we have x prime is equal to 4, 1, 6, negative 1 times x. So 4 minus lambda, 1, 6, minus 1 minus lambda. Is this the same problem we just did? Oh, okay. Whew. For the moment. The determinant. So it's 4 minus lambda times negative 1 minus lambda minus 6. So
when you factor it, it'll be like the same thing as the last problem, but if you're doing the matrix thing, it comes out to be different.
oh, the eigenvectors?
Yeah.
Oh yes, because we had 2 and 3. Okay, fine. This is, but still it's way too close to the previous example. All right, so I'm just going to then steal the previous answers so I don't have to grind through this. Lambda squared minus 3 lambda. Minus 10 equal to 0, from where lambda 1 was what? 2? Negative 2? And lambda 2 was 5? Is that what we get? Anyone? Negative 2 and 5? Yeah? And now, for lambda negative 2, we have 6 and 1 and 6 and 1. Nice. Times AB equals to 0, 0. So we can see that we are using 6A plus B equals to 0, from where 6A is negative B. So if you pick A to be 1, then B is negative 6. So we have our first eigenpair. New word. Lambda 2 is equal to 5. So negative 1, 1, and 6, negative 6. Times AB equals 0, 0. So we have that negative A plus B is equal to 0, from where A is B. So just use 1, 1. And the overall answer X is immediately C1. Vector for this one was 1, negative 6. E to the negative 2t plus C2, eigenvector 1, 1. E to 5t. Ta-da! Just use the eigenpairs carefully, plug everything in. I'm sorry? When is the exam? Oh, in 2 days?
Yeah.
Oh, wow. All right, let's take a look. What's so there is more for this. So we'll finish this lecture the next after the exam, because we will have maybe 30 minutes, which will be enough to finish this lecture. What happened? Yeah, I'm gonna put like 6 power series and 3 of these. Yes, it's gonna be done in a second. All right, so let's review for the exam, and then we'll. So exam next class, right?
So we come in at 6
All right, bye, stream.